Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 3 of a unit Kinetic Theory of Gases. So let's begin with today's class. In today's class, first we are going to discuss about the types of the molecules. So let's begin. When I say different types of molecules, we say that a molecule is the smallest particle in a chemical element or compound that has the chemical properties of that element or compound. That means from that molecule you can understand complete property of that compound as well. There are different types of the molecules. One, it's a monoatomic molecules. Another, it's a diatomic molecules. One more, it's a polyatomic molecule. So these are the different types of molecules. Let's see and observe them one by one. First, it's a monoatomic molecules. It is a molecule having a single atom. Having a single atom is called as the monoatomic molecule. And when I say mono, it words represents mono. It says having only one atom. Let's take in case of an helium. So this is the molecular formula He, and it is having only the one atom. When it is having only one atom, that is what we call as a monoatomic molecules. Now let's take a case of diatomic molecule. It is a molecule having two atoms. That is what we call as the diatomic molecule. Let's take a case of carbon monoxide. It is having two atoms. Let's take a case of hydrogen gas. It is having the two atoms. So all those which are having two atoms are considered as a diatomic molecule. Next, let's suppose, even look at this, that when I say diatomic molecules, when I say a diatomic molecule, it is known as the linear diatomic molecule because both atoms are present on the same line. It is a rigid molecule as elasticity is not present, and this is the kind of the diatomic molecules. Now let's look at this diatomic molecules. This are known as, when we take a case of carbon monoxide, this is the known as the non-linear diatomic molecule because different atoms are present. So if same atoms are present, same atoms, it's a case of hydrogen gas, H and H would be there. And then when same atoms are present, they are the linear diatomic molecules. But in this case, it's a case of carbon monoxide. Carbon and oxygen has been connected. When these two are connected, this is what we call as the non-linear diatomic molecule. And this can be said as non-rigid molecule because elasticity is present over here. I hope this is clear. Now let's take the next. It's a polyatomic molecules. What is it? A molecule having n number of atoms is called as the polyatomic molecules. Let's take in case of CO2. It's a carbon monoxide. Here n is the number of atoms. So when I understood a CO2, when I understand it would be a CO2, more than two elements, more than two molecules are present. That's why we can consider it as an polyatomic molecules. Let's look at this. It's a two oxygen and one of the carbon would be connected in this manner. So here it's an O, C and O. This two non-linear diatomic molecules because different atoms are present. I hope this is clear. You already have learned this and you studied this in your chemistry classes as well. But this is the requirement of the physics. So we just rush to it and have a content of it. Let's go for the some quick questions. In diatomic molecules, linear diatomic molecules have, yes, in that linear diatomic molecules have same atoms. If they are having a different atoms, then they are called as the non-linear diatomic molecules. Please keep this in mind. Second, linear diatomic molecules are blank molecules. Linear diatomic molecules are, when I say linear diatomic molecules, they are the they are the rigid molecules as they are not having any elasticity. Next, In non-linear diatomic molecules, blanks are the present. Yes, different atoms are present when we talk about the non-linear diatomic molecules. Next, in non-linear diatomic molecules, the molecules present are non-rigid, elastic. Yes, this both are correct. Both A and B. This should be correct, and this would be the situation. I hope this is clear. Now, we have learned and we have studied up till now about the molecules. Now we are going to study the motion of these molecules. So let's begin with the types of motion, that which kind of motion this molecules can do. Let's have a look. When I say motion, when we say motion, that we understood that motion is change in position of a body with respect to surrounding. So if a body is changing its motion with respect to surrounding, then we say that it is the just it is the object is in motion. Types of motion that can be possessed by a molecule. There are three types of motion. One, it's a translational motion. Second, it's a rotational motion. Third, it's a vibrational motion. So our molecule can have this kind of motion. It could have a translatory motion, or it could have a rotational motion, or it could have the vibrational motion. Now let's begin with translational motion. In translational motion, the molecules travels in a straight path. Therefore, it only exerts kinetic energy, and their kinetic energy could be given as it's an 1 by 2 into m into v square. This is kinetic energy of the molecule, and this is the translational motion. Now, next is the rotational motion. In the rotational motion, the molecule rotates around a fixed axis. It also exerts a kinetic energy, and that kinetic energy is what we call as a rotational kinetic energy. This rotational kinetic energy could be given as it's a 1 by 2 I omega square. Why? Where I is the moment of inertia and omega, it's an angular it is angular speed of rotation. This is half I omega square. Next, third one would be the vibrational motion. When I say vibrational motion, in vibrational motion the molecule oscillates, and when it oscillates, it is having kinetic energy as well as potential energy. So in vibrational motion, it is having kinetic energy and potential energy. It could be written as kinetic energy plus potential energy, where kinetic energy could be written as half mv square and potential energy could be written as half kx square. I hope you understand and you remember this. It's a half kx square. X is the displacement while k is the spring constant. So connection between two molecules can behave as a spring. It is something like that. So it is having two motions. When I say it's a vibrational motion, that means it is going to have a two motion. It is having kinetic energy as well, it is having the potential energy as well. Now let's look at the summary of this motion. A translational motion is there in which molecules travel in a only straight path, and its kinetic energy could be given as half mv square. In the second case, rotational motion is there. In rotational motion, molecules rotate around a fixed axis only. And when I say it's a rotate that in rotational motion molecules rotate around a fixed axis, this is what we call as an half I omega square. Next is the vibrational motion, and in the vibrational motion molecules perform the oscillation, and when they perform oscillation it is half mv square plus half kx square. I hope this is clear. Is it clear? Is it clear? Do you have any doubts in this? Is there anything? No? Let's look at the quick questions. In translational motion, the energy exerted is given by, in translational motion, the energy exerted is given by it's in half mv square. Only translatory motion. In rotational motion, the energy exerted by the molecule, yes, it's in half I omega square only. Only rotational motion, no translatory motion. Next, in the vibrational motion, the energy exerted by molecules is given as it is half mv square plus half kx square. I hope this is clear. Is it clear? Is it clear? Now let's discuss law of equipartition of energy. When we say equipartition, then we understand this is equal division. This is about equal division. It is having a very significant meaning. Let's have a look. So this is, we are going to discuss about the law of equipartition of energy. Let's begin. We can say that a molecule is free to move in space, needs three coordinates to specify its location. Yes, we have a coordinate system, Cartesian coordinate system, and in that system as well, we, if I want to define address of anything, that we call as a reference vector, or then we must have its x dimensions, y dimensions, and z dimensions. So if it is constrained to move in a plane, it needs two coordinates, and if someone is constrained to move in a single line, then it needs just one coordinate to locate. So motion in a body as a whole from one point to other is called as a translational. And if a molecule is free to move in space, then it is having three translational degree of freedom. It is having three translational degree of freedom. Now, when we used to have VRMS, have you remember it? Have you remember it? What was it? The VRMS was equals to under root of 3 kbt by m. I have used small m, that's why I can use the kb. Otherwise it was under root of 3 rt by m. Yes, so this v square rms is equals to 3 kbt by m. I hope this is clear. Yes, so this is m into v square rms is equals to 3 kbt, and if I divide this 1 by 2 on both the sides, this half mv square rms is equals to 3 by 2 kbt. Now look at this. If my molecule is there, let's suppose it is a single molecule, and if single molecule is there, then it could not rotate around its own axis. I hope you understand this. But it can definitely translate in x-axis, in y-axis, or in z-axis. I hope you understand this. So this half mv square, this is the kinetic energy, and this total kinetic energy is 3 by 2 kbt. That can be distributed in this 3. But in which direction, what to distribute? That whether I need to distribute a more content in x, whether I need to distribute more content in y or z. So law of equipartition, as I said, it's an equal division. Why division would be equal? Because when we go through the assumption of the KTG, we used to study that particle will be having a random motion in nature. That's why you don't know that in the next instant particle will move in the x direction or in y direction or in z direction. As you don't know, you are going to divide this into three equal parts. So if I'm going to divide it into three equal parts, every dimension, I could say so, it's a half mvx square could have the energy of half kbt. Same is true for the half mvy square and half mvz square. So we see that in thermal equilibrium, the average of such term is half kbt. So a molecule which is free to move in a space has three translational x, y, and z. These are the translational degree of freedom. I hope this is clear. Is it clear? Is it clear? This could be also considered as an another way, that each translational degree of freedom contributes a term that contains square of some variable of motion. that would be half mv square that we have already discussed. They have represented it as a cx square, and similar terms can be represented as in cy and cz. So we can say that it has 1 degree of freedom for motion in a line, 2 degree of freedom for motion in a plane, and 3 degree of freedom for motion in a space. So if some object is there, which can move only in plane, let's take an ant, case of an ant. Can it fly? Can it fly? I said no. Does it move on a straight line only? I will say no. Let's say this is x, this is y. It can move in this plane. So degree of freedom of this ant will be 2. I hope this is clear. But let's say honeybee is there. Let's say honeybee is there, which can fly as well as move. So it can move in xyz, but it is not going to rotate around its own axis, that you understand. So this honeybee has a 3 degree of freedom, and this ant is having 2 degree of freedom. I hope this is clear. Is it clear? Is it clear now? Do you understand what degree of freedom is about? Do you? Are you sure? Let's have a look. It says that the molecule is having 2 rotational degree of freedom, if it is having, each of which contribute the term to the total energy consisting of translational energy and rotational energy. So first, it is having a translatory energy, that is half mcx square plus half mcy square plus half mcz square. This and this is the form of the translational energy. And let's suppose it is going to rotate around its own axis, then this and this is the rotational kinetic energy. Here I1 and R2 are the corresponding moment of inertia that we have already discussed, and omega 1 and omega 2, this two are omega 1 and omega 2, this two are the angular speeds. I hope this is clear. So let's switch to the degree of freedom. This all topics are somehow related with each other, and that's why its a flow is something like this. So let's understand what degree of freedom is. Have a focus. This is very important topic as far as we are concerning with the kinetic theory of gases, as well as we used to learn thermodynamics. Please have a focus on it. So what is degree of freedom? We say that when gas molecules are in motion, they have particular type of freedom, which is known as the degree of freedom. And which kind of freedom is there, we will see. So degree of freedom tells us about the type of motion in the gas molecule. So look at this. This gas molecules are there. There is a collision also there. There is a collision with the container as well as molecule as well. So they are having certain specific kind of motion. And if you can observe that each molecule is a single molecule. Each molecule is a single molecule. So it is moving in X, it is moving in Y, it is moving in Z. I hope this is clear. So let's understand the degree of freedom. There are the 3 different kinds of degree of freedom would be there. One of them was translational degree of freedom. In the translational degree of freedom, molecule can travel in straight line only. But when I say only in straight line, then it means it can move in X, Y and Z only. I hope this is clear. You are not going to move X and Y, that means in a plane. But this is allowed. Definitely this you can move in X, you can move in Y, or you can move in Z. Next, it's a rotational degree of freedom, in which particle is going to rotate around a fixed axis, and that would be equals to half I omega square. This is second degree of freedom. And the third, it is the vibrational degree of freedom. In vibrational degree of freedom, it is going to oscillate. In vibrational degree of freedom, it is going to oscillate. One would be half mv square, another would be the half kx square. So when gas is in motion, it is displaced in a straight line, or it rotates, or it performs oscillation. It could have This three, maybe all of this, maybe one of them, or maybe two of them motion, and from that motion we can identify the degree of freedom of particular molecule or particular gases. I hope this is clear. So now let's understand the degree of freedom and let's discuss it particularly for gas to gas. Let's suppose we begin our study with monoatomic. So when I say it's a monoatomic gas, let's suppose it is having a single molecule only. It is having a single molecule only. It can have either motion in X, it can have either motion in Y, it can have either motion in Z. So this is having translatory, or I should say translational degree of freedom. It's a 3. How? Either X, either Y, either Z. Now it's a translational. Now let's talk about the rotational. So this is molecule and this is axis. Does it rotate around it? In reality, if you observe the molecule, it is something like this. Can you see this? Yes. So can it rotate? I must say it's in half. It's in half. When I write moment of inertia, it's that moment of inertia could be written as m into x square. In this case, perpendicular distance is 0. So please do remember this. No molecule can rotate around its own axis. I'm talking about the molecule. No molecule could rotate about its own axis. So translational degree of freedom 3. Rotational degree of freedom, I'm talking about the monoatomic, it's a 0. Same way vibrational degree of freedom of monoatomic gas is 0. So total degree of freedom of the monoatomic gas, total degree of freedom of the monoatomic gas, it's a 3 plus 0 plus 0, it's a 3. I hope this is clear. Yes, we are going to discuss such motion of every gases. Let's have a look. Second is the diatomic gas. Second is the case of diatomic gas. So let's understand that it is a dumbbell like structure, and when this is a dumbbell like structure, this can move in X, this can move in Y, or this dumbbell like structure can move in Z. So translational degree of freedom will be 3. Let's check rotational degree of freedom of this system. So for rotational degree of freedom, what I need to observe is that let's suppose this is X, this is Y, and this is Z. So as you observe that this both the molecules are on X, so it could not rotate in X. I due to X is 0, I due to Y. You can see that this rotational axis, it is rotation something like this rotational axis passing through this, but this molecule can surely rotate, so Iy would be something. And let's talk about the Iz. Again, this rotational axis, it will try to rotate something like this. So this is not going to rotate, but this is going to rotate. So this is again yes. So for the diatomic gas, rotational degree of freedom will be 2. And last but not the least, vibrational degree of freedom. Vibrational degree of freedom, yes, it is 2. But this is generally seen, this could be generally seen at higher temperature. If temperature is normal, this cannot be seen. So it is 5 plus 2. This asterisk represents its It is available at the higher temperature. If temperature is lower, it could not be seen. I hope this is clear. Is it clear? Are you sure? Great. Next would be the polyatomic gases. Next is the polyatomic gases. In polyatomic gases, we have two segment. One is the linear polyatomic gases. So let's first discuss the linear polyatomic gases. Let's suppose it is the structure of something like this. So this all can move in this direction x, y, and z. So for the polyatomic gases in the linear, if it is a linear gas, then translational translational degree of freedom, it is 3. Can it rotate? Let's have a check. That let's suppose this is on x-axis, so they are not going to rotate because all the molecules are on the same rotational axis. Let's suppose y-axis has been passing through this, so yes, they can rotate across it. Let's say z-axis has been passed through this, then this molecule could not rotate, but this too can rotate, so this can rotate. So translational degree of freedom, it is 3. Next, it is the case of rotational degree of freedom, it is 2. Vibrational, again with due conditions applied at higher temperature, it would be 2. So again, this will be 5 plus 2. I hope this is clear. This is linear polyatomic gases. I hope this is clear. Is it clear? Is it clear? This is linear polyatomic gases. And if this is linear polyatomic gases, next would be the non-linear polyatomic gases. It's a non-linear polyatomic gas. So what would be the situation in non-linear polyatomic gas? Let's understood that this is the structure of molecule, let's suppose. So first thing, do they move in x, y, z? I must say yes, they can move in x, y, z. So from this it's a translational degree of freedom will be the 3. Can it rotate? Let's check that. Let's suppose my rotational axis passes through here, and this is I, y. I should say yes, it can rotate. This is y. If I pass my rotational axis from here, it's an x. Even this too, this and this could not rotate, but this could rotate, so I must say ix, yes. And if I pass my rotational axis from this, let's say this is iz, then this and this is not going to rotate, but this is going to rotate, so I must say it's an iz. It would be yes. So from this it's a rotational degree of freedom, that would be equals to 3. And again vibrational degree of freedom, it would be 2, but again with conditions, and that condition is at higher temperature. So again, this is 6 plus 2 with stars. I hope this is clear. If it is at higher temperature, it would be having that degree of freedom, and it is always 2 in numbers. But if it is at the normal temperature, it does not have any degree of freedom associated with it. I hope this is clear. Great. Now let's look at this degree of freedom. It's just the summary sheet. That let's suppose the gases is monoatomic. When the gas is monoatomic, translatory degree of freedom is 3. Rotational degree of freedom, monoatomic does not contain. Vibrational degree of freedom, monoatomic does not contain. In the diatomic, let's suppose we have two different cases. One is the linear, another is the non-linear. And when if one is linear, another is the non-linear, then translatory degree of freedom is 3, rotational degree of freedom 2, and vibrational it does not contain. While in the case of the non-linear, while in the case of the non-linear, it is having a translatory degree of freedom 3, rotational degree of freedom 2, and vibrational degree of freedom it's 1, or that means it has been 1 by 2 kbt multiplied by 2, which is kbt. Next, let's discuss about the polyatomic gas. Let's discuss about the polyatomic gas. What would be the situation in polyatomic gas? When I say it's a polyatomic gas, then it's a translatory degree of freedom. Translatory degree of freedom will be the 3. The rotational degree of freedom will be the 3, and vibrational degree of freedom. Vibrational degree of freedom will be F. F is the number of degree of freedom that we have represented. I hope this is clear. Is it clear? So do you have any doubts up till now in the concept of degree of freedom? Do you? Do you have anything? No? Great. So let's look at this. It's a translational degree of freedom. Translational degree of freedom is present in diatomic molecule. Yes. Polyatomic, do they contain this? Yes. Monoatomic molecule? Yes. So all of the above contains a translational degree of freedom. Next, rotational degree of freedom. Rotational degree of freedom is present in that diatomic molecule, yes. Polyatomic molecule, yes. So it contains in both A and B. Next, vibrational degree of freedom is present in linear diatomic molecule, no. Non-linear diatomic molecule, yes, at higher temperature. Polyatomic, yes. So both B and C. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you have any doubts up till now? Is there anything? Is there anything? No? So let's work for the questions. Suppose question says that find out total energy possessed by monoatomic gas. So what I need to do is, from degree of freedom, we must understand that according to the law of equipartition, of energy, each degree of freedom contains half kbt energy. I hope this is clear. So I understand that monoatomic gas is having only translatory motion. So monoatomic gas is having a 3 degree of freedom. Yes, it is only the translatory. So the total energy would be equals to 3 multiplied by half into kBT. Total energy of monoatomic gas. Do you understand this? Have you? Have you got this? Ready for the next question? Great. Let's suppose in the next question they said that find out total energy possessed by diatomic gas at normal temperature. So what I need to do is, now I understood that each degree of freedom possesses an energy of half kBT. I'm talking about the diatomic gas. So in the case of diatomic gas, it is having a translatory 3 degree of freedom. So energy associated with translatory degree of freedom, it's a 3 by 2 kBt, and and it is having a rotational, it is having a 2 degree of freedom. So energy associated with it, it's a 2 into half kBt. So the total energy is equals to energy due to translatory motion plus energy due to rotational motion. So this is equals to 3 by 2 kBt plus 2 by 2 kBt. This is equals to 5 by 2 kBt. This is the total energy of diatomic gas at normal temperature. Here we have ignored the effect of vibrational degree of freedom because they have said at normal temperature. I hope this is clear. Now let's suppose the question says that find out total energy of polyatomic first linear and second non-linear gas at at normal temperature. Let's say this is the situation. You need to find out the total energy of polyatomic. First it would be a linear and then the non-linear gas at normal temperature. So what I'm supposed to do is, let's begin with the linear. For linear gas, let's suppose we have two motion, it's a translatory and rotational. For translational, degree of freedom is 3, and for rotational, degree of freedom is 2, as it is a linear. So energy associated with this, it's a 3 by 2 kBt, and energy associated with this, it's a half kBt. So total energy would be equals to 3 by 2 kBt plus half kBt. This is equals to plus 2 by 2, sorry. So this is 2 into 1 by 2. Yes. So this is 3 by 2 plus 2 by 2. It's a 5 by 2 kBt. I hope this is clear. And let's talk about the non-linear. Let's talk about the non-linear gases. So in the case of a non-linear gases, it's a translational and rotational. Degree of freedom, this is 3 degree of freedom. Rotational, it is having 3 degree of freedom. So the total energy of translatory motion, it's a 3 by 2 kBt. This is again 3 by 2 kBt. So when I am going to add this, this is 3 by 2 kBt plus 3 by 2 kBt. This is equals to 3 by 2 plus 3 by 2, it's a 3 kBt. This is the total energy. Possessed by a polyatomic gases. I hope this is clear. Is it clear? Are you sure? Great. So let's just wind it up the session over here. This was all about the types of molecules and degree of freedom. Before you tune in to the next lecture, please go through this very carefully, because when we are going to start the new lecture, we are going to use this total energy concept of each molecule. I hope this is clear. So please revise it, thoroughly. This will help us to understand the next lecture in a much better way. Thank you. Have a good day. Take care. Bye bye.